Welcome everybody to this Biophotonics lecture on FLIM and FRET. So here you see a slide showing the content of this lecture. We're going to start with explaining what is FLIM, Fluorescence Lifetime Imaging Microscopy. Then we deal with the different methods of how to measure FLIM, boxcard, TCSBC, frequency domain, and then a section on Förster Resonance Energy Transfer and how it can be measured via FLIM, and finally some notes on time-resolved anisotropy measurement, also called rFLIM. So I want to remind you first about the Jablonski diagram of a fluorophore. So here you see the ground state, often called S0, and the excited state called S1. We're going to start with the vibrational ground state level here and excite to this typically higher vibrationally excited state in the electronic S1 level. So this is due to the Franck-Condon effect. And we have a picosecond time decay, a very fast decay to the vibrational ground state of the S1 level, followed by a very slow decay, which is the fluorescence decay. And because of that decay here, and finally also another picosecond decay in the electronic ground state, we've twice lost energy. So that's why we have a redshifted fluorescence compared to the excitation wavelength, which is of course called the Stokes shift. So what you see in this diagram, I've indicated the typical rate constants that matter. So if you consider this to be one state and this to be a second state only, then we can interpret these sort of lines here, these arrows, as kinetic sort of arrows that indicate the rates. So that means the K excitation rate here would be somewhat proportional to the excitation irradiance or intensity, and proportional to the absorption cross-section of your molecule. So that means this transition here is proportional to that rate, whereas this rate is intensity independent. It's purely defined by the lifetime tau. So 1 over the lifetime defines that rate here. So how fast does your electronically excited state decay? And for simplicity, we've left away the picosecond rates here. Of course, you could write that down also as rate equations, but typically you do not see that in a measurement because this is a nanosecond decay, whereas this is a picosecond decay. So we have a factor of about 1,000 between these two different lifetimes of the states. So what you would measure if you now observe the fluorescence that comes out is actually a product of this rate here, how many photons per second you send out, and the probability that you are in the excited state. And because there's this proportionality and it's not going to change within the time scale of the fluorescence emission, what we're really monitoring is something that is proportional to the population of the S1 state, so the electronic excited state. And so what you get is this typical exponential decay curve, single exponential decay being E proportional to e to the minus t over tau, tau being the fluorescence lifetime, its inverse being the rate here, and t being the time of your measurement. Of course, the problem is that this would require an incredibly fast sampling, and there's no sampling technology available, at least not easily, that can sample these times at these time scales continuously. And so for that reason, you have to do some tricks, which we will be going in later. So now the thing is that this simplified system in reality doesn't exist like that. And the first thing is that in addition to this thing which is called the radiative rate, so that's if the fluorophore has only one channel of decaying that is by radiation, by sending out some radiation, then this would be describing the radiative rate. In reality, there's an additional rate, so we get the fluorescence lifetime this way. But in reality, there's more rates. So for example, the S1 state can also decay or make a transition via intersystem crossing to the triplet state. And there will be some later intersystem crossing back to the singulate state, which is actually called phosphorescence. It's an emission of radiation here. And of course, there's also a non-radiative decay channel. That means there's some internal conversion that allows the electrons to lose their energy via other channels, vibrational channels, basically a transition via conical intersection or something like this, into a highly excited vibrational state of the S0 state. And this way, the electron can get rid of its energy as well, or the molecule if you want. And so this additional channel will quench the overall fluorescence lifetime. So tau refers basically to the combined rates here as fluorescence lifetime, whereas the red arrow refers only to the radiative rate as such, which would then be something that you can compute from pure physics reasoning, and which is also interesting. There's a formalism that's called the Strickler-Berg formalism that tells you how to do this, but this is not going to be the topic of this lecture. If you're interested, you can read about it. So what you see is that the typical fluorescence decay curve, which would be looking like this if you didn't have any additional rates, then gets modified to a shorter lifetime via all these additional channels of decay. So that is the non-radiative decay channel, and for example, the intersystem crossing into this direction, and in fact also other effects like Förster Resonance Energy Transfer, which is another channel for the fluorophore to get rid of some energy via Förster transfer to another molecule, and that also quenches the fluorescence lifetime. So you call this quenching because when the lifetime is sort of reduced, and that would also reduce the overall brightness of your fluorophore, which is proportional to the integral of this fluorescence lifetime decay curve. Well, so now we are asking, how can you actually measure such a fluorescence lifetime decay curve? So if in reality the fluorophore decays like this, or the measured photons would sort of decay in brightness over time, over the time span of a few nanoseconds, the question is, how do you measure that? And one approach is that you have some way that you can, for example, gate your detector. So that would be like this. You can, for example, have a multi-channel plate where you can have some high voltage, and with some complicated electronics, you can actually very quickly turn up the high voltage and also turn it down again. And if you manage to do that quickly enough within the time scale of less than a nanosecond or something like this, or in the range of nanoseconds, you can measure by repeating this experiment. You do a pulse excitation and then followed by a gated detection. And this way you're going to average over multiple measurements. Typically, you're going to get an average of the brightness. And you then do that with a shifted box card, like this, and another one, and another one. And so what you finally get, you can say, is a convolution of the original curve with your box function. And the funny thing is, if you convolve an exponential with anything, it turns out that it still stays an exponential with the same lifetime. So that means we can directly read off the lifetime by knowing how much we shifted this nanosecond decay. You might wonder how you can shift this. Of course, there's electronics means for doing that, but basically in old times, you could do that also by just changing the length of a cable. Because one thing you should remember, 1 nanoseconds with speed of light corresponds to 30 centimeters roughly. Right? So by just changing the cable length a little bit, you can already delay here the box card. As I said, in reality, you do that slightly different with some electronics, but basically that's the trick that you could do. So you might wonder now, is this curve really what we want? And it turns out in most respects, it's the same of what you want to measure, even though you're convolving. However, there's some differences, and I'm going to show you this in the next slide. So I should mention before I go to the next slide that there is something about this which is not very good. That means in every measurement, as you saw, we are only integrating this fraction of it. Let's say 10% of the overall emitted photon count. And that's of course very bad, because then you're throwing away 90% of your photons and you're measuring only 10%. And as you might know, we are very photon starved in fluorescence imaging. So in this way, we are losing a lot of our very precious photons, and that is a big disadvantage of the boxcar approach. But an advantage is you can be fairly fast because you can acquire this with a multi-channel plate, for example, over the whole field of view simultaneously and get reasonable throughput of photons. And so that means you don't have to wait forever to get a good fluorescence lifetime image. So, as I said, a box does not change the decay time, however, and that means also that the curve remains single exponential if you're starting with a single exponential curve. And of course, you have to be careful with the start of the curve when you're integrating this. But if you start your fit, for example, late enough, or if you make sure that the box starts only after the full excitation, after the excitation pulse has finished, then you should be fine. What you have to be careful with is the amplitude ratios. That means how bright does your sample appear will not be proportional any longer, which has to do with this integration effect, and you would have to correct. And so here's some theory that shows you how big this error would be. So if you see this is the relative size of your box delta T compared to the fluorescence lifetime. So if we are at a box that has already the size of the fluorescence lifetime, we are essentially making an error in the relative amplitude that we are measuring by 35% or something like this. So the recommended bin size, therefore, is a 5-fold smaller box size than the shortest component of the lifetime, which of course then means that your efficiency is rather low because you are most of the time discarding most of the photons. So how do you actually build something like this? Well, here you see, for example, a titanium sapphire laser to generate the pulses that are used for excitation of your fluorophores. Then this is run via multiple lenses or a Nipkow disk system or something like this, as it is shown here. And then this confocal-like system illuminates your sample. The light goes back and is then imaged onto what I said, a gated CCD camera. So this is the multi-channel plate system that allows you to gate your signal. That means every photon, it hits at a certain time, and either the voltage is high, then these photons get amplified, or if the voltage is low, they basically get dropped and you're losing them. And this is done with time windows in the nanosecond range. And so as you see, via a trigger mechanism, you're actually gating this CCD, and you're having a delay unit that allows you to then steer how much delay you get from between the excitation pulse and the detection window that you allow the CCD to see light. It turns out that some CCDs are nowadays so fast that you can use the clocking from an interline CCD from the interlines, or from the sensitive area to the interlines, and you can do this with a dual tap so that you can clock them into 2 different interlines, and you can then use this for some sort of box cut approach. This has a great advantage in terms of efficiency because the multi-channel plate detectors, which are essentially for every pixel a tiny little PNT, they are rather inefficient. However, the problem is that the speed of these devices is not yet quite fast enough to really work in this range of 1/5 of the nanosecond. So it's rather in the range of, I think, tens to hundreds of nanoseconds that you can do this gating. So they are not really well suited for fluorescence, but rather for phosphorescence, which is more in the microsecond range. So here you see an example of a phosphorescent dye, which is europium DDPA, a particular component, and you see some crystals here, and you see while we are now changing the delay time of this box, we detect the signal goes down, and you then plot this, you can very nicely see this single exponential decay of this fluorescence, or rather phosphorescent component. So europium is one of these rare earth substances which have a forbidden inner shell transition, and that's why their lifetimes are relatively long. But if you see here it says milliseconds rather than nanoseconds. So this makes it particularly easy to work with this. You could almost use a standard CCD for this. Certainly these CCDs if you want. This is now in the nanosecond range. So here you see a pollen grain, and you see the typical lifetime of autofluorescent components in a sample. And as you see here, we have decay components in the range of nanoseconds, but if you look closely, even quicker components in the hundreds of picosecond ranges. And so if you try to fit this curve and you do your observation very, very carefully, you find that you have at least 3 multi-exponential components in there. Note that the y-axis here is a logarithmic axis. So this therefore allows you to, you've actually measured this over orders of magnitudes in brightness, right? So you're going from something very bright right after excitation down. Yeah, and you see also that there's other problems here. Before the actual lifetime measurements, you get stray reflexes from the tube lens and so on. Because the tube lens comes before your sample, the reflex will appear earlier than the actual start of the curve here, and therefore it's not really disturbing your measurement if you know about it. And you just make sure that you're starting your fitting somewhere here, or if you dare it, you can include the instrument response function of the system and start really at 0. So the maybe most well-known technique is called time correlated single photon counting. And what I've shown you here is the excitation light is given by a pulsed laser with a regular pulse interval. So if you have, for example, an 80 megahertz laser, then you get every, I don't remember what is, 12.5 nanoseconds or something like this, you get a pulse of excitation. And now you would think that you would be waiting for the photons to come. And you see here a typical sort of graph of when photons might be appearing. In reality, actually, they're much rarer than it is shown here. And now the problem that you have, if you build such a system, you can use a photomultiplier, for example, or an avalanche photodiode and try to time the photons. So naively, you would think, okay, let's start a timer here at time 0 when the pulse is there, and then wait for the photon to come. And if the photon clicks, it will just basically stop the timer like a stopwatch, and then you read off the time and store it somewhere. So this would be a very sensible approach. The trouble is this: the dead time of the time to amplitude converter is 125 nanoseconds. So if this is 12.5, so it's basically every 10 pulses you can start a measurement. So if you did such a scheme, that would be terribly inefficient, because you would start a measurement, then measure nothing until the next pulse comes, and then you have to wait for 9 more pulses until you can start the next measurement. So it's only 10% efficiency also in detection. That would be terrible. So what you do in reality is slightly different and much smarter, which is you're using the photons, in fact, as the start of the stopwatch. So if a photon comes, and as I say, they come very rarely and much rarer than these pulses are, then this photon would start the stopwatch, and then the next pulse would be the stop signal. So you're using this time delta here from the photon arriving to the next pulse, and use that as your timing. Of course, it's slightly less precise because there might be a little bit of jitter between these pulses, but it turns out these come from a coherent laser cavity. It's extremely precise here, and so you can completely neglect this jitter, and you can get a very precise timing. And this way you are very efficient, because as long as your photon's coming rare enough, you can capture every single photon, because you just have to make sure that no second photon arrives between start and stop, and that is relatively improbable if your rate is not big enough. And so you're using this, what is called reverse mode operation, that you measure the time from photon to the next laser pulse. And of course, then you just display this inversely and you can then read off your fluorescence decay time. So here you see sort of a very schematic setup. You have a pulse source, you're exciting, in this case, a cuvette here, and then with a photomultiplier to you're measuring, and as I said, you do this inversely, but it's now displayed forward just for visualization, and you get your lifetime curve. And so if you do that in an imaging setup, for example, in a confocal laser scanning microscope, you do this measurement for every single pixel. And what you see here is that you can then plot, for example, the fitted fluorescence lifetime in every pixel from such a curve that you've measured. And as you see here, there seem to be two different particles. So these are plastic beads, essentially, if I remember right, or some liquid droplets or something like this. And they are two different kinds. So the small ones are one type of material, and the other ones are another one. And note that you can tell them clearly apart from their fluorescence lifetime, even though that the intensity you measure, so the color of the dye, might be exactly the same, yet you can tell them apart by their lifetime behavior. If you just looked at the brightness, you wouldn't be able to do that. They might be brighter or less bright, or even the same brightness. However, with looking at the fluorescence lifetime, you are able to tell them apart. And so this is maybe also one of the strongest points, that fluorescence lifetime is essentially completely independent of intensity. And so you're avoiding confusion by brightness changes because you're looking at an inherent property of the dye, which is its fluorescence lifetime decay curve. So you can then plot this again in a logarithmic plot. And if it's a single purely mono-exponential decay, you would expect a nice straight line in such a semi-logarithmic plot. And indeed, this looks like to be true in a very good approximation. It's a little bit curved, which is probably because there's a little bit of an offset background on this whole thing, and that you have to account for in your fit. And you see here very nicely the very different lifetimes, 3.65 nanoseconds compared to 2.25, 1 over e time. And here's another measurement where they've looked at what happens when you do laser-induced fluorophore deposition. So you're basically making sure that the laser induces some deposition of these fluorophores, and depending on the process, how this happens, you can now see that you get multi-exponential decay times. There's a long-range component, 3.4 nanosecond, and short range, 1.4 nanosecond, and the relative concentrations of these changes. If you look here, what is called the abundancy maps, if you are unmixing the signal into these two components, you can see, we have the one type of material deposited like this, whereas the other type has not really changed very much, except this hole in the middle that you've burned into it. And here is some more biologically motivated studies. So there's a dye called D as red. And what they did here is they compared the D as red dye lifetime with GFP. You would at first expect them to be fairly similar, but it turns out that D as red has a very interesting fluorescence maturation effect. So that means it takes a relatively long time for the dye to be processed in the cell until it is really mature, like a good whiskey or a good beer or something like this. And during that time, the D as red actually changes the lifetime. You do not see that here. You just see one example, which is already an H D as red, which has a 1.5 nanosecond lifetime. But if you look at the rest of this paper, it will tell you that the lifetime really matured from 2.8 nanoseconds down to 1.5 nanoseconds while it's getting older. And so you can use this to learn something about processing of these dyes inside your cell. Whereas actually EGFP over the whole time span pretty much stays constant at the same lifetime. So I want, here's a small note on the problems that you have when fitting single or multiple exponents to such curves. So one thing is you have to be careful with this initial start of your experiment, because at the start, if there's a little bit of leakage through your filter, then you have also at this very position the excitation pulse in it. So what is called the instrument response function, taking the excitation pulse and maybe the jitter in your detector together, that convolves in and is one thing, it convolves the whole curve, which, as we discussed before, doesn't really change the curve in itself. However, if you have a breakthrough of this, so some non-filtered material, you get this extra peak of fluorescence at zero, which is a problem. And this would be accounted for is another problem, which is algorithmic problems or background problems. So usually you have some dark counts of your detector or some leakage of the system, room light coming through or something like this. And so you have to be really careful to account for the statistics of the background, because otherwise you're going to perform pretty bad at the sort of long lifetime part of your curve. So that's the word of caution. And so here you see a pretty good fit of a lifetime curve. However, so this is very convenient to show FLIM plots on the semi-logarithmic scale. However, you have to be really careful to not perform a fit on the logarithmic scale. And the reason for this is shown in the next slide. So as I say here, fitting in the lin-log plot is not a good idea. You can use it for display though. And the reason has to do with this effect. The logarithm is a very nonlinear transformation that you're doing to your data. And if you imagine you have a certain mean value of measurement of intensity, for example, or lifetime or whatever it is, and with the spread of it, then the transformed way would look like this. So this is pretty much okay. However, if you're then sitting at the very low range and you have this mean value with a spread, you see that this nicely symmetric Gaussian curve gets deformed in a very non-symmetric statistic. And in fact, this would lead to a bias. So that means when the mean is here, you would expect it to be here, but when you actually measure it from the transformation after having done the log transformation, you would get a different mean. So this is called a bias effect. Therefore, be careful. Try to avoid any nonlinear transformation when you're doing the fitting. And so mathematically, you can say in this range, it's pretty much okay because the derivative stays more or less constant of this curve. However, here it's pretty bad because it doesn't. So this is a general thing that I also tell people in image processing. So never compute the average of pixels in a computed image. What I mean by that is here shown as an example of a squaring operation. If you have in reality some value that fluctuates around 0, positive and negative, and then you take the square, then you see the mean should be really 0 of this fluctuation, and therefore the square of the mean should also be 0, but because you've transformed it with the square before taking the mean, you're actually getting a biased value here, right? So the mean of this curve is not 0 anymore. And so if you can always basically first average things together and then calculate the rest, that would mean in these lifetime things, you would first take the raw lifetime curves in a certain region of interest, then you average these curves together, then you're fitting this one average curve, and you can then display this lifetime that you get. And this will be a different result than fitting all the individual pixel curves and averaging the lifetimes together, which will bias you if you do so. So be careful. And there is an exception, which is for everything that is linear computation. So you can prove that for any linear operation, it doesn't matter whether you're first taking the average and then computing your linear transformation, or first transforming and then computing the average. However, another word of caution, never clip at 0. So if you, for example, clipping away the negative intensities, then you're again getting biases. So we've now seen the box card. The TCP-SPC stands for time correlated single photon counting. So that was the second method of measuring the lifetime. And now I'm introducing the third method called the frequency domain fluorescence lifetime imaging microscopy. So how does that work? Well, it is based again on this multi-channel plate intensifier, which is coupled to a CCD camera. So that basically can take a whole image, photons in, converts them to electrons, which get amplified in this device, pixel by pixel, and again converted into light with the scintillator screen that will then be re-imaged or even fiber coupled to the CCD camera. And so what you now do to efficiently operate this MCP intensifier, rather than with a boxcard approach, what we do is we use a sinusoidal signal generator. For example, at 57.7 megahertz, we're running this oscillator, and that oscillator at the same time drives the intensifier, and it also sort of drives a second signal generator, which then influences an AOM. So here we have used a frequency divider, so to divide the frequency by 2. So that means if this oscillates with 57 megahertz, this oscillates with 28.5 megahertz, and the second signal generator drives the AOM. Why do we need this division? Because the AOM is an acousto-optical modulator, and basically that generates a deflection every time that, so it's a standing wave that you're generating, and this standing wave is oscillating at the frequency that you're driving it with, but twice per oscillation it causes diffraction, and twice per oscillation it basically goes through the zero line, where this just looks for a brief moment of time like a piece of glass. When you're at the zero line, then you get a maximum zero order through. When you are at this at the positive or negative amplitude of this thing, then it's deflecting the light up to almost 100%. And this way, what you've done now is this way basically you double the frequency again. So we first had to divide it just to double it again, so that in the end we have an oscillation at the same frequency of 57.68 megahertz here. And here you can use a CW laser, a continuous wave laser, an argon laser, for example. And so here we have now our sinusoidally modulated light with the help of the acousto-optic modulator. And it basically flashes with a sinusoidal intensity distribution over time our sample. Now the sample takes that intensity and responds to it by convolving its fluorescence lifetime decay curve over time with that excitation intensity. So if you convolve a sine curve with anything, it will remain a sine curve. And we are convolving the sine with an exponential decay that starts at time 0. And so what will that lead to? I will show you that in a second. And the light then goes back. And so it's basically still flashing a little bit after being modulated by the fluorophore now. The fluorophore, one thing that it will do is will introduce a time delay on average. And this time delay you will then pick up. And what you now do is you have this intensifier being driven by the same sinusoidal wave. And if you assume this to be linear, you can just get more signal when it's just bright, and you're also amplifying it than when it's dark and you're amplifying it, because then there's nothing there to amplify. So if you then phase step this intensifier by introducing a delay here, you can record an image for every phase of the MCP intensifier. So get over the relative time distance or the relative phase between excitation and emission, you can record an image. And so this technique is called a homodyne technique, because homodyne means that your frequency of modulating your signal and the frequency of modulating your detection, they're the same frequencies. That's why it's called homodyne, for the same frequency. And you're phase stepping it, so you're acquiring several images. There's also another technique called heterodyne, where you just detune that frequency a little bit, and then you're quickly measuring. So in effect, it's really the same thing, whether you detune the frequency with a heterodyne technique, or you just keep the same frequency with homodyne. It doesn't really make a big difference. It's just a different way of thinking about it. So here I show how this looks like. So the fluorophore sees this sort of curve over time of excitation intensity, and you see that it is very bright when it's in the intensity excitation maximum at that time, and it's of course very dark in these minima here. So what will now happen is this convolution with the exponential decay. So it would basically give after certain times of these curves, right? That's because the one that's excited here, they all get delayed a little bit and reduced in amplitude. And if you're summing all these curves together, what you will observe is this thing. So it is a curve that still is a sinusoid, because it turns out whatever sine curve you're adding to a second sine curve, it will just modulate the amplitude amplitude and the phase, right? If the second curve is the same, then the amplitude is double and the phase is still the same as before. If the amplitude is, for example, just pi relative to this, you would get you would get an intensity or an amplitude of 0, and if it's slightly less than pi, you get a pretty big phase shift of pi half in this case, and so on. So what you can get is this modulated curve, and you can characterize this curve by two things. That's the curve of emission over time now, but that's not what we measure. We then have this detector gain, which gets multiplied with it, right? So we are sending the same original curve to the detector, and it would multiply the curve like this. And if you now calculate the integral of this multiplication, you get a certain value here. And then we are phase shifting the detector gain. And what you now see is we get a measurement that looks like this. And this measurement essentially reproduces this curve, except that it still down modulates it a little bit by this second sort of integration with the sine curve. But you therefore get now this curve, and from this curve you can determine two things. One thing is called the relative phase shift between the excitation position in phase and the maximum of your homodyne detected signal. And this is related via this equation here to what is called the phase fluorescence lifetime, so tau phase. And there's another parameter you can measure, which is the modulation depth of this curve. So delta over the mean intensity of your curve. So that's the relative modulation. If this is 1, you have a perfectly modulated curve. If this is 0, it's just a flat line, nothing left. And it turns out if you assume a single mono-exponential decay, you can go through the math and you get these two equations here. So this would be the phase modulated lifetime, and this would be the amplitude modulated lifetime. That's denoted with tau m for the modulation depth. And yeah, you can calculate from these two factors, the modulation factor here and the phase, the relative phase shift. You can calculate these two lifetimes, and you would expect them to be the same if it is a mono exponential fit. And it turns out that this is what you typically do in a single frequency homodyne detection, single frequency frequency domain lifetime measurement. And by comparing these two measures, we know if they are the same values, then we have most probably a mono exponential decay, and we're kind of happy and we think we understand everything. And if they are different, we don't know very much, except that it's not a mono exponential decay. So here you see an example of a convallaria rhizome sample, and how these images look like in a multi-channel plate camera when you have different phase shifts between excitation and the MCP modulation. And as you see, while you're doing this phase stepping, then this sample seems to become really dark and really bright again. And from this we can use the tau phase and tau mod. And as I said, if it is a single component, single exponential decay system, then they are the same. If it is a multi-component system, turns out that tau mod is expected to be bigger than tau phase. So how do you data process this? Well, you're Fourier transforming along the stack of images. So that's just a trick of how to determine best the modulation degree and the relative phase, because then you can just look at the first order harmonic peak of this Fourier transform, and it automatically gives you the complex value degree of modulation and phase, essentially by comparing the 0 order to the first order peak, the degree of modulation, and by looking at the phase of the first order peak, you know what is your phase. And then with the equations that I've already stated, you can calculate tau phase and tau mod. So you're correcting for the reference modulation and phase shift. There's some correction factors to apply, and you compute the modulation and phase lifetimes as described. So with this, I've described to you how FLIM works technically, and now we are going to look at a few applications. So the first very important one is Förster Resonance Energy Transfer, and you've seen already in the talk by Daniela how this actually works, but I'm going to repeat the basics of it. So Förster transfer, sometimes, well, people also call it Fluorescence Resonance Energy Transfer, but you should really avoid this. It's a misnomer. It should be called Förster Resonance Energy Transfer. That's what the F stands for. So what happens if you have a fluorophore that gets excited by some fluorescent light? It's now in the excited states and gives off its excited light. And that's what you would normally measure by the Stokes shifted emission of radiation. However, if there's a second fluorophore close by that can also be excited, so that one is called the donor because it donates its energy to a second molecule that's called the acceptor, then what happens is that if you have a spectral overlap of the emission spectrum of the donor with the excitation spectrum of the acceptor, then what can happen is that instead of emitting the light here, you get much less emission from the donor and you rather get excitation, which is called sensitized emission now, because the donor helps the acceptor to absorb that green light and then emit the red light. So that's called acceptor sensitization, and the whole process is called Förster Resonance Energy Transfer. So at a first glance, this looks like it's really a process of the donor emitting some light and the acceptor absorbing the light. It turns out that this is really not the case, and it doesn't quantitatively, that would not really describe what you're observing. Most easy to see is the fact that if you look at the polarization characteristics, that the donor and acceptor would best sort of re-emit and reabsorb the light if the two dipoles would be parallel at a certain distance. But it turns out that the most efficient Förster transfer you get if the if the two dipoles are parallel and they are sitting sort of in the same radial plane, being orthogonal to their dipole orientation, transition dipole orientations, I should say. However, in Förster transfer, it is actually the direction when they are parallel and they're sitting behind each other that gives you the strongest transfer. And so this is completely not explainable if you just look for far field emission. You would have zero emission in that direction because the dipoles only emit orthogonal to their orientation, whereas the best Förster transfer you get when they are in the same line. Yeah, that would not be explainable otherwise. And you really need to go a little bit deeper into near field effects and quantum mechanic, basically coupling of these systems, and then you can understand how you get this, what is called radiationless energy transfer between donor and acceptor. And nevertheless, you need the states to be able to emit and absorb if you want. And this way, the spectral overlap integral is very important. Here you see graphically, for example, a cyan molecule on the top left, and it has some binding or some partner that it is fused to, and now a second molecule that is typically dark because it's not excited by the blue light. However, if we now make them bind, and that doesn't mean that the GFPs bind, but it's rather these molecular parts that have interaction site, so they make these two proteins bind to another, and because the fluorophores are dangling off the same molecules, you now suddenly get this sensitized emission from this molecule. So here this could be YFP, for example, yellow fluorescence protein. And you see an example in reality here. So we have a Golgi from monkey kidney cells, and with a transmembrane fusion protein, and you see that if you have a CIFP, so that's also called cyan, and YFP filter set, then you can see in the cyan filter, you can see, for example, these components, and if you have both filters on, where you see both channels, you see these components, and you can then see, well, they are not proportional to another. So just by rationing them together, you can see that these are really much less bright in these channels. And so there's a reduced donor lifetime here, and therefore also a reduced donor brightness, what you can see here. So this is an indication that there might be Förster transfer going on, but it's not a clear proof yet just by the brightness, because there could be tons of different other effects changing the molecular species, for example, salt concentrations, similar things that can massively change the fluorescence lifetime of species. So it turns out if you most importantly, not only could the lifetime be changed, but most importantly, you can have, of course, brightness changes of species simply by their relative presence being different. And so if you look here, then there is no change actually of lifetime if you measure here, whereas the brightness is clearly different. And in these ones, you have a reduced tau, which indicates that most probably there's Förster transfer going on. So how do you get more confirmation that this is really Förster transfer going on? And so what many people did is the following trick. If you have such a situation as first shown, Förster transfer going on, and then you're bleaching the acceptor, that means you destroy the ability of the acceptor to accept the energy from the donor, then you would expect that you see an increase in brightness of the donor. And so that is a relatively good sort of mark that there is really Förster transfer, or rather there was Förster transfer going on when you did the first experiment, because it's a little bit harder to explain this increase of brightness with another effect. And so this is called donor fluorescence. It's called acceptor bleaching, this method. So you're bleaching the acceptor and you're looking for an increase in brightness in the donor, or even better, an increase in lifetime of the donor, because the fluorescence lifetime in the Förster transfer situation of the donor was quenched. And when you then deleted the Förster transfer because you bleached the acceptor, then you should see an increase in brightness and an increase in the fluorescence lifetime of the donor. Turned out that this is a nice idea, and it was used a lot over many years, but it is still not 100% safe that you didn't do mistakes there. And the problem is that it turned out that with intense illumination like you do for the bleaching, you can actually also cause photoconversion of dyes. So you can have something like a red dye, and by putting lots of light on it, convert it into something like a green dye. And so you get this apparent increase in brightness. And in reality, it's not necessarily really a Förster transfer, proof of Förster transfer. And of course, this is much better and safer if you're using lifetime measurements, but it's still not 100% error prone. And so for my taste, the best is actually to look for what is called the acceptor rise in your FLIM signal. So if you're looking for the acceptor and you're seeing it's not immediately responding to the light given to it, but it takes a little bit of time to first accept the light from the donor, then that's the best proof you can ever get, because it's really hard to explain any other effect than Förster transfer for getting you this this slower rise of the initial signal. The problem with that is, of course, if your transfer efficiency is very high, it's very hard to detect this very short time of acceptor rise. I'm going to go back into the acceptor rise a little bit later. And what you see here is some data where this acceptor bleaching has been performed. And so you see here the signals in the two channels, cyan and YFP here before bleaching. And when we now perform the bleaching, we are destroying the fluorescence in this box region, destroying the fluorophores, the acceptors there. And at the same time, as you could see here, was an increase in the donor fluorescence. And you see also in the overlay this increase of the donor. So I want to now spend a little bit of time to tell you how to actually model Förster transfer species. And because there's even in the literature some sort of misconceptions of how you would do that. And what I'm showing you first is the misconception, and then I'm going to show you how to really do it. And so naively, you would think the following. You have a donor species and you have an acceptor species, and we have a state of the donor being in the ground state. So I labeled it D as 0 because S0 is the ground state, the electronic ground state of your molecule, and D stands for donor. And here we have donor excited state, the S1 state of the donor, and of course we have the same for the acceptor ground state and excited. So we get transition rates. So this transition rate constant is called K excitation, and I put a D to mark it for the donor, and of course this would be proportional to the incident intensity somewhat. And then you have the decay rate that we talked about earlier, which is essentially the inverse fluorescence lifetime that you would have here. And this itself consists of various rates, for example, the non-radiative and the radiative rate, and then also maybe the triplet rates in the system crossing. And you have the same thing for the acceptor for different wavelengths. And now we want to model the Förster transfer, and naively you would think, what do I do now? It's a bit difficult, but you typically draw something like this. So what that means is basically while the donor decays, this decay of the donor kicks the acceptor into this excited state. And you see already by this graph that there's something fishy about doing this. And so then when this would be the Förster transfer rate that is written down here as K fret. Remember, K is always 1 over a time, how long it takes. Yeah, it's a rate in how many events per second would be happening if you are in this particular source state. Then this would basically tell you the rate of transitions into the destination state. Okay, how do we write this down? Well, we write down a series of differential equations, which I've done here. So this sort of notation means population of that state, or you can also interpret it as probability of being in that state. Either way, both is fine, but if you think about this as a population of the state, maybe it's easier to understand, but either way. So the change of each of these states is given by the probability to be in that state times the transition rate plus. And so as you see now, to be able to somewhat describe this Fret effect, we have now a funny situation. What I put here is the Fret rate, but the Fret rate has two requirements. Not only do we need to be in the DS1 state, but we also do need to be in the AS1 state, because Förster transfer cannot be happening if we are in the AS0 state, if we are in the AS1 state. If we are in these two states, there's no Förster transfer possible, because this one, the acceptor cannot accept any more energy. It's already excited, right? And so to reflect that, I put here essentially the product of the probability to be in this state and in this state. So product of probability DS1 and AS0. And yeah, you see that's already problematic, because this is not any longer a linear differential equation system, what you have here. So you can now go through these equations. If you stop the talk, you can work out yourself whether they are correct. I might easily have done some error when cooking them up, but I tried at least to do the right thing. And so it's pretty simple to write that down. You just go through all the different transitions, take source and destination, and decide whether there should be a plus, meaning an influx to this, or a minus, an outflux from here, for example. And you put all the terms down. Right, so as I indicated, this is all wrong. And the reason is that we didn't clearly enough think about what is a state. We have a system, and the system here is a system that does not only concern a donor separately from an acceptor, but it's a system that concerns a donor and an acceptor. That's why we have to rethink the whole thing in a slightly more abstract way, but then you'll get, interestingly, linear equations, and they are more correct. So this is the solution to the problem. So rather than going with these bubbles indicating a state of a molecule, now we have a combined state. So that means each of these bubbles here indicates what state is the donor in, and that's the first index, and what state is the acceptor in, that's the second index. So this would be S00 state, which means donor is in the ground state, acceptor also in the ground state. So what can we do now? Well, for example, we can do K excitation donor to push the donor in the excited state, whereas the acceptor still is in the ground state. And then there can be an emission from this state back into the donor ground state. And we can also, from the same state of this two-molecule system, say, well, we excite the acceptor only. then we are in this state. Donor is in the ground state, acceptor in the excited state, and we can have emission of the acceptor only to be back in the ground state. But of course, we can also do this. We can be in the excited state of the donor and then excite the acceptor. Then we are in the state where they are both excited. And then there can be a donor emission, then we have only an excited acceptor, and so on, right? So these are really the states. So very important, remember, if you have combined systems, think about the combined states, right? And write down all the equations for the combined states. So, and now Förster transfer is the following thing. It's going from the S10 state to the S01 state. So we start with donor excited when we do the transition, and now this transition doesn't depend on any other states. It requires donor excited, acceptor not excited. We have a certain rate of transfer depending on the distance. And if you learned in Daniela's talk, there's an inverse 6th order dependency with the distance between the two molecules, but that's not the topic of this talk here. Then you end up in the acceptor excited state and donor not excited state. And for example, you can end up by an acceptor emission, which would then give rise to your acceptor curve. So then you can write down the equations for this. I hope they are correct. And as you see, they are now all linear equations. Interestingly, they all have like 3 state concentrations or state probabilities in there. However, the last equation has 4, right? So this is, in this case, this one, because there's more arrows here than everywhere else. You see 1, 2, 3, 4, 5 arrowheads appearing here. Maybe I have to double check that. Okay. Yeah, so this one depends on the concentration of all of 3 of these, whereas this state, when it emits, it does not depend on this concentration. So that is why this one has 1 term less than the other ones. Right. So if you then model this and you try to fit your data, you see here a typical acceptor system where you get now a curve from the donor lifetime measurement as well as the acceptor lifetime measurement with the TCS. And now the really interesting thing is twofold. One thing is, as you know already, that the donor has now a faster decay than it would normally have. So let's say without Förster transfer, it would decay like this, slower. Now we have a faster drop. And so this is the quenching effect of the donor, reduced lifetime of the donor via the extra decay channel, which is the Förster transfer that can make the donor give its energy away quicker than usually. But much more interesting to me is this thing, the acceptor rise. So the fact that the donor starts with a really like kink curve here, whereas this one is a slow rise at the beginning. Well, slow, still very fast because it's a high transfer efficiency. But you see this rise here. And in my mind, if you want to prove I had Förster transfer, this is really the best proof, because I cannot imagine any other effect other than Förster transfer or probably Dexter transfer, so another type of energy transfer, to give rise to this effect that you see an acceptor rise before it actually decays. So any kind of molecular transition or something like this would not have this effect. They would just lead to changes in lifetimes, but not to an acceptor rise in the lifetime decay. So to summarize this, if you bleach the acceptor, you're losing the Fred de-excitation path and you're increasing the donor lifetime. And here is another image that shows you this. So this is a frequency domain lifetime image, and you see here tau phase and tau mod, and both of them have this sort of increased lifetime. In this case, for this box where the bleaching was performed previously, the bleach subregion. And so you can be pretty sure now that this is really a Förster transfer that was going on. Here you see an example of a molecule that has the ability to reversibly change upon UV radiation from one form into another form, and with visible light it basically converts back into the original form. And both forms have a different spectrum, as you see here by the absorbance spectrum, but of course they also have a different fluorescence emission spectrum. But here it's important that one of them can actually absorb and act as a Förster transfer acceptor, whereas the other form does not. And so you can reversibly switch between the two states, and that allows us to perform acceptor bleaching experiments, but instead of bleaching we are reversibly switching back and forth, which avoids the potential in the interpretation for a slowly converting effect of one of the dyes. You can then make measurements repeatedly by switching the acceptor back and forth. So it's as if we could repeat the acceptor bleaching experiment many times, and you can then be really sure that no photo conversion or something like this is going on with the donor to explain the changes in lifetime sense. Here's a side remark. So what you see here is single molecule FRET measurements. So you're doing single molecule measurements of the lifetimes, and you see this interesting effect, how the relative ratio of intensities changes with the lifetime change that you see at the same time. And you see as the lifetime goes longer, you also have a brighter emission, and if the lifetime goes shorter, you have a shorter emission. And in this particular case, it's interesting because it's single molecule experiments. You can identify 3 clusters in these sort of double 2D histogram, and these are different forms of the molecules that can exist. So there's basically an open form, which is the donor only, where the molecule is not bound to its acceptor. So these are RNA molecules. Here you have the doublets being formed, but it's not yet conformationally sort adjusted to a final position. And so in this case, if a protein then binds in addition to this RNA, you can actually change the relative again, because you're changing the conformation, and you can clearly see that in the lifetime as well as in the absolute brightness of the single molecules. So you have these two things going on at the same time: donor quenching and donor lifetime reduction. So the final part of the talk is anisotropy FLIM, so fluorescence lifetime imaging microscopy in combination with polarization measurements can give you information about anisotropic things, and that can be quite interesting because molecules rotate over time, and you can observe these rotation over time because it is in a similar sort of time range for some molecules than the fluorescence lifetime decays. So how would you do that? Well, you know about polarization. There's S and P polarization of the electromagnetic field, and if you have here, for example, a cuvette, you're exciting it with one particular polarization, S polarization, and then you can detect either S, like before, or P polarization if you're rotating your analyzer in this particular case. Then from these measurements, you can then calculate this factor called anisotropy. And so this looks really strange. If you would think about how you would normally do that, you would think, okay, that makes sense. I want the contrast of this measurement. So I take I parallel. That means when the analyzer is parallel to the polarizer or to the excitation field direction, and you're subtracting the perpendicular direction, and you would divide by the sum of it. That would be the normal thinking. But you see here the equation is slightly different. You see that it's a factor of 2 there in the I perpendicular. And I want to understand a little bit where this factor of 2 comes from in this anisotropy equation. And if you think about it, well, R would be 1 if your sample is 100% polarized, and it would be 0 if it's completely unpolarized. Interestingly, if the molecules are randomly oriented, it turns out that this factor R is 0.4. So what I mean by this, imagine they're all static, so they are not moving over time while they decay. However, they're randomly oriented, and then you have a certain probability of exciting something that is not in S and not in P, but somewhere else, and you have a certain probability of detecting it. And if you work out all the maths and all the integrals of this, you arrive at R is equal to 0.4. Interesting number. So what about this factor of 2? So if you think about this, you're doing this with typically with a situation like this in a microscope. So you're exciting your dyes like this, but then you're detecting light only in the reverse epi direction here, and we cannot put an objective sideways or something like this, and we would. So if we work out what happens there, the problem is that the dipole is not able to emit when it is in the Z orientation. You see, if the dipole sits along Z, then it would have zero emission along the direction of detection. Yet they do, of course, do that, because a diagonal dipole will also emit in this will have the possibility to emit in it, but we cannot see it. And so if you think about it, the object emits as much undetected light in the Z polarization as it would emit in the Y polarization. So if we start with X polarization, we have a certain chance of it emitting in Y polarization, but the same amount we should also expect in the Z polarization. However, we don't detect it with our objective. And that is why the I perpendicular here is multiplied with a factor of 2 to estimate the total emitted light, because we're not detecting that. Yeah, but we are only interested in the Y polarization in the denominator here. So that's only Y polarization, but this is Y, and the estimate of Z polarization is the total intensity. And that tells us the total anisotropy, what we are interested in. Well, what about high numerical aperture objective? Because then everything changes a little bit. So if you have very high NA, then you're picking up some of the Z polarization as well, because it goes this way. And so these equations wouldn't be really valid anymore. And that's why fluorescence anisotropy experiments are usually performed with relatively low numerical aperture objectives, or they are calibrated in such a way that you can get rid of this effect. So here's a quick sort of drawing of the rFLIM setup. So it's in this case again a frequency domain setup with the higher frequency for driving the intensifier, and the lower frequency being doubled again by the AOM to drive at the same frequency the excitation source, and then you can do the phase stepping and so on. And of course now, in addition to the filters, we have an excitation and emission polarizer, solar polarizer, and an analyzer. And again, you measure tau phase and tau mod from your homodyne measurement scheme. And now you can calculate, in addition to tau phase and tau mod, also this ratios, AC ratio and DC ratio for parallel to perpendicular, and you can work out more things with that. And as you see here, if we now look at tau mod and tau phase, and we look at that with different concentrations of glycerol of a particular dye, fluorescein, you can see by changing the concentration of glycerol, we seem to be changing the apparent lifetime in the parallel and perpendicular channels. That is interesting, yeah. So the reason is that the glycerol concentration influences the rate of rotational diffusion. So how quickly do they actually turn? And that makes a difference in this particular case. So you see that at 10% we have a different tau mod and tau phase than at 61% glycerol. So to summarize, we have learned Förster transfer is sensitive for very small distances. Well, I mentioned that in passing. Fluorescence Lifetime Imaging Microscopy is a great help for measuring Förster transfer reliably. And FLIM methods are the boxcard approach, the TCSBC, time-correlated single photon counting, and the frequency domain approach. So there's extensions of FLIM. I didn't talk about them a lot, but there's also a sectioning version of FLIM with confocal microscope. There's rFLIM, as you've seen. There's a spectroscopic version of it as well, which shows you the lifetime of every spectroscopic component of every emission wavelength separately. But with that, I'm at the end of this lecture, and I'm looking forward to our discussion on next Friday. I would like to thank finally Thomas Jovin, Quentin Henley, and Philip Oesterheld for providing data and discussions and talking with me lots of time about FLIM and fluorescence lifetime imaging and the various methods, anisotropy, rotational diffusion, and so on. So thank you very, very much.